Most people, when they first encounter this question, do the mental math without realizing it. The moon is 384,000 kilometers away. Apollo got there in 3 days. So, if we point a spacecraft at Mars, the nearest planet, maybe a week? 2 weeks if we take it slow? Here is what that intuition misses. At its closest approach to Earth, Mars sits 56 million kilometers away, 146 times the distance to the moon, and Mars is the easy one. By the time you reach the outer planets, you are measuring the journey not in months, but in years, sometimes decades. But the distances alone are not the real story. By the time we have traveled through every planet in this solar system, you will know the actual travel times, and more importantly, you will understand why those times are what they are. Because the solar system is not a set of fixed targets, it is a machine. And navigating it requires learning to think like the machine thinks. Before we map any routes, we need to talk about why the question is harder than it first sounds. Planets do not orbit the sun in circles. They travel in ellipses, stretched ovals, which means the distance between any two planets is constantly changing. Sometimes they sit on the same side of the sun, close. Sometimes they are on opposite sides, separated by the full span of the solar system. There is no single distance to Mars. There is a range. Your launch window determines where in that range you are starting from. This also means pointing a rocket directly at a planet is almost always wrong. By the time you arrive, the planet has moved. The correct technique is called a Hohmann transfer, a flight path shaped like half an ellipse that leaves Earth's orbit and meets the target planet's orbit at exactly the right moment. Picture it like throwing a pass in football. You do not aim at where the receiver is standing. You aim at where they will be. The Hohmann transfer is the most fuel-efficient route we know how to fly. The cost is time. There is one more tool, the gravity assist. A spacecraft swinging close to a planet can borrow a fraction of that planet's orbital energy and exit the other side faster than it arrived, without burning a single gram of extra propellant. It is the closest thing spaceflight has to a free lunch. Voyager 2 used 4 of them chained together. Without that sequence, a mission to Neptune with current propulsion would require more propellant than any rocket we have ever built could lift off the ground. That is the frame. Ellipses, timing, borrowed gravity. Now let us start with the planet closest to the Sun and the one that breaks the first assumption. Mercury is the solar system's first counterintuitive fact. It is the closest planet to the Sun and among the most difficult to reach. The scientific case for Mercury sits in its deep interior. Its metallic core is enormous relative to its size, roughly 85% of the planet's radius, compared to about 55% for Earth, and it generates a magnetic field that, by rights, a world this small and this old should no longer possess. That field is a key to understanding how rocky planets differentiate and evolve. Its crater-saturated surface, essentially unchanged since the violent early period roughly 4 billion years ago, holds a geological record that Earth's plate tectonics long since erased. Water ice in permanently shadowed polar craters, traces of ancient volcanism. A planet that kept receipts the rest of the solar system threw away. Getting there is a problem of energy, not proximity. Mercury sits deep in the Sun's gravitational well, which means any spacecraft heading inward from Earth is constantly being accelerated. To stop at Mercury to not blow straight past it requires shedding an enormous amount of speed. In space, braking costs exactly as much propellant as accelerating. The mission record tells that story precisely. In 1973, Mariner 10 used a Venus gravity assist and reached Mercury in about 6 months as a flyby. It could not stop. Messenger, launched in 2004, required 6.5 years and 7 gravity assists, threading through Venus and Earth, to arrive slow enough for orbital capture. Bepi Colombo, the joint European and Japanese mission launched in 2018, is running an even more elaborate choreography and will not settle into Mercury orbit until 2025. 6.5 years to reach the planet closest to the Sunday. The solar system does not grade on proximity. Moving slightly farther out from the Sun, though still firmly in the inner solar system, brings us to a world that looks, at first glance, like everything. Mercury is not. Venus is the brightest object in our night sky after the Sun and the Moon. A signal, as it turns out, that tells us almost nothing about what lies underneath. It matters because Venus and Earth began from nearly identical raw materials, in nearly the same region of the solar system and ended at completely opposite outcomes. Earth, temperate oceans, complex life. Venus, a surface at 465 degrees Celsius hotter than Mercury, despite being farther from the Sun under an atmosphere pressing down at 92 times Earth's surface pressure, laced with clouds of sulfuric acid. The leading theory is a runaway greenhouse effect that may have triggered after Venus lost its oceans. Understanding exactly when and why that happened is not an academic exercise. It is the closest thing we have to a controlled experiment for what a planet looks like after the climate goes irreversible. Transit times to Venus have historically been among the faster missions in the inner solar system. Mariner 2 completed the first successful planetary flyby in history in 1962, reaching Venus in 110 days. Pioneer Venus in 1978 took 198 days on a slower, more fuel-efficient approach. The European Space Agency's Venus Express in 2005 made the journey in 153 days. The variance 110 days to nearly 200 reflects entirely how much speed you need to shed on arrival. Fast approach, more braking fuel. Slow approach, longer travel, less fuel. Every mission makes that trade differently depending on its objectives and mass budget. The Venera landers, which are the only spacecraft ever to transmit images from Venus's surface, add useful context for what awaits. The most durable one survived 127 minutes. The combination of heat, pressure, and chemical corrosion made anything longer structurally impossible with 1980s engineering. The record has not been broken since. We have not tried again. When the destination is Mars, the question changes. It stops being purely scientific and starts sounding, cautiously, like planning. Mars is the one world in the solar system where the phrase human mission appears in government budget documents and serious engineering timelines rather than purely in theoretical papers. The reasons are legitimate. Mars has a day 24 hours and 37 minutes long, polar ice caps of water, evidence of ancient rivers, lake beds, and possibly a northern ocean. A thin atmosphere 1% of Earth's pressure, mostly carbon dioxide that is thin enough to be a challenge and thick enough to complicate landing. If microbial life ever existed beyond Earth, Mars is the most probable location where remnants survive. That is the scientific consensus that has directed billions of dollars of missions since the 1960s. The distance range is significant. In 2003, Mars came within 55.76 million kilometers of Earth, the closest approach in nearly 60,000 years. At its farthest, that separation reaches roughly 400 million kilometers. The average is about 225 million kilometers, which works out to a light travel time of roughly 12.5 minutes, meaning any signal sent to a spacecraft near Mars, or any command sent to a rover, takes that long each way before it arrives. Using a standard Hohmann transfer with current chemical propulsion, the transit runs 7 to 9 months. NASA's Mars Reconnaissance Orbiter, launched in 2005, took just under 7 months. Curiosity's spacecraft took 8.5 months. A full crewed mission transit out, surface stay of 14 to 18 months, waiting for the next favorable alignment. Transit back runs roughly 2.5 to 3 years from Earth to Earth. The biological challenge of that duration is real and unresolved. Deep space outside Earth's magnetic field exposes crews to cosmic radiation at rates that meaningfully increase long-term cancer risk. Estimates vary, but a 2-year Mars mission delivers a dose of roughly 0.66 sieverts against a career lifetime limit for NASA astronauts of about 0.6. Bone density and cardiovascular function degrade in microgravity. These are solvable engineering problems. They have not yet been solved. What shortens the trip is higher thrust. Nuclear thermal propulsion, which uses a fission reactor to heat hydrogen propellant instead of chemical combustion, could theoretically cut Mars transit times to 3 to 4 months at equivalent payload. The technology exists in prototype form. No operational system has been flight tested in space. That gap is currently the central planning problem for crewed Mars missions, not the rockets, not the life support. Mars represents the edge of the destinations we have a credible near-term path to reach with humans. Beyond it, the scale changes character not just in distance, but in what any mission must solve. Jupiter is where that shift becomes concrete. The scientific priority is 3 of its moons, Europa, Ganymede, and Callisto. All three likely harbor global liquid water oceans beneath their icy crusts, kept liquid by tidal heating as Jupiter's immense gravitational field constantly flexes and squeezes their interiors. Europa's subsurface ocean is estimated to contain more liquid water than all of Earth's oceans combined. Its surface is laced with fracture patterns, suggesting active geology. A thin oxygen atmosphere is generated continuously by radiation, splitting water ice molecules at the surface. If we are searching for life beyond Earth, Europa is the most credible address we currently have. Jupiter sits between roughly 590 million and 970 million kilometers from Earth. The light travel time from Earth to Jupiter at average distance is about 43 minutes. The flyby times are fast. Pioneer 10, the first spacecraft to reach Jupiter, arrived in about 640 days, roughly 21 months, on a direct trajectory. Voyager 1 made it in 546 days. But these missions passed by. They did not stop. Stopping at Jupiter requires a completely different approach. Galileo, launched in 1989, took nearly 6 years to reach orbit not because it could not go faster, but because arriving at Jupiter too fast means flying straight past it. To slow down enough for orbital capture, Galileo looped through a Venus flyby and 2 Earth flybys, gaining speed in carefully calculated directions to arrive at precisely the right velocity. Juno, currently returning extraordinary data on Jupiter's magnetic field and interior, launched in 2011 and arrived in 2016, 5 years. Europa Clipper, NASA's dedicated Europa mission, launched in October 2024, will reach Jupiter in 2030 after a 5.5-year transit. It will not orbit Europa directly. The radiation environment around the Moon would destroy its instruments within weeks. Instead, it will fly past Europa repeatedly from a safer Jupiter-centered orbit, accumulating data across dozens of close passes. Human missions to the Jovian system are not in any credible near-term planning horizon. The radiation environment near Europa delivers a lethal dose to an unshielded human in approximately 10 minutes. Shielding adds mass. Mass demands more propellant. Propellant extends transit time. The compounding works against you in every direction. Jupiter stretches the definition of reachable. Saturn stretches it further, and then Cassini spent 13 years there, making the case that the investment was worth every year of the journey. Saturn. The ring system spans 282,000 kilometers from inner to outer edge while averaging about 10 meters thick. If you scaled those rings to the width of a piece of paper, the paper would be 5 kilometers wide. How such a structure forms, how it is sustained against gravitational disruption, and when it will eventually disperse, these questions remain unresolved. Titan, Saturn's largest moon, has lakes and rivers of liquid methane and ethane, a thick nitrogen atmosphere, and organic chemistry complex enough to invoke serious discussion of whether it might harbor life in a form entirely unlike Earth's. Enceladus vents plumes of water vapor, salt, and organic compounds from its south pole directly into space, essentially offering a sample from its subsurface ocean to any spacecraft passing nearby. Saturn ranges between about 1.2 billion and 1.7 billion kilometers from Earth. Pioneer 11 arrived after 6.5 years. Voyager 1 reached it in just over 3 years, aided by a favorable alignment. Voyager 2 took 4 years. Cassini launched in 1997, arrived in 2004, spent 7 years in transit, threading gravity assist through Venus twice, then Earth, then Jupiter, all to arrive at the exact speed required to enter Saturn orbit without flying past it. It spent 13 years studying the system before being deliberately steered into Saturn's atmosphere in 2017, a decision made to protect Enceladus and Titan from Earth contamination. Cassini's dataset is still being analyzed. In a meaningful sense, we are still at Saturn. Beyond Saturn, the solar system becomes a place we have barely visited. 2 worlds lie out there that most planetary scientists consider among the highest scientific priorities in the field, and that, between them, have received exactly 1 close-up spacecraft visit each, both in the same decade, both by the same probe. The ice giants are classified differently from Jupiter and Saturn for good reason. Their interiors are dominated not by hydrogen and helium, but by a dense, high-pressure fluid of water, methane, and ammonia. In surveys of planets orbiting other stars, Bodies in this size range between Earth and Neptune are the most commonly observed type of planet. Understanding how Uranus and Neptune formed is, in part, understanding the dominant planet type in the galaxy. Uranus tilts at 98 degrees. It orbits the Sun, essentially rolling on its side, like a ball rather than a top. Its magnetic field is offset from its rotational axis by 59 degrees and displaced from the planet's center by about 1/3 of the planet's radius, implying an internal structure unlike anything else we have observed. Uniquely among the giant planets, Uranus radiates almost no internal heat, a behavior that may trace back to a massive ancient collision that disrupted its thermal layering. We have visited each of these worlds exactly once. Voyager 2 flew past Uranus in January 1986 and Neptune in August 1989. That mission was possible because of a rare alignment of the outer planets that repeats approximately every 176 years. Voyager 2 was launched in 1977, specifically to exploit it. The leading candidate for the next dedicated mission, a Uranus orbiter and atmospheric probe, ranked the highest priority for outer solar system exploration. In the most recent Planetary Science Decadal Survey, anticipates a launch in 2031 or 2032 and a cruise time of roughly 13 years using a Jupiter gravity assist. First data from Uranus orbit, approximately the mid-2040s. That is not a planning failure. It is an honest accounting of what orbital mechanics requires. Neptune is farther still. A direct trajectory to Neptune orbit with chemical propulsion runs 12 to 15 years, and no favorable planetary alignment currently on the horizon replicates the chain Voyager 2 exploited. The science case is compelling. The path is not yet clear. Which brings us to the world at the outer edge of the known solar system, the one we have visited once, briefly, and whose surface surprised everyone who saw it. Pluto orbits between roughly 4.4 and 7.4 billion kilometers from Earth. The light travel time from the Sun to Pluto ranges from about